Okay, good morning, everyone. So today I will basically describe about the two techniques. One of them that we already have in the speed facility, and the other one we are just getting in a couple of months. So first of them is about the accelerated mechanical mapping, where you can do a pretty high speed mapping of any type of structures, microstructures, interfaces. And then the second technique is mostly about the integration of a AFM and Raman system along with thirds and scattering near field optical microscopy. So I will do some basic fundamentals, and also I will also discuss some of the applications of these techniques and the different components that we are getting. Okay, so before I go there, so there are brief description about some of the instruments in the speed facility that we have in Hanuman Center. The top left, you see we have a conventional dimension icon systems where you can do up to 12-inch wafers. Is a fully automated stage, and then it can do a lot of these functional AFM, also basically electrical, mechanical type of measurements along with the normal surface structures. And then the bottom left is a high-speed version of that, where it's a fully automated system and you can do almost 1 frame per second. So basically, you can do multiple samples in a pretty short span of time. Then in the middle section, I will describe about this Raman a little bit in more detail. And then we also have a life science imaging systems where it's integrated with the fluorescence microscopy. So you can do a lot of these nanomechanical properties of cells, tissues, and all those things. And then we also have a conventional indenter system where you can do nanomechanical analysis in terms of the hardness, modulus. You can also do the nano DMA, dynamic mechanical analysis. Basically, you can measure the lost and storage moduli. And then we also have the soft indenter, where you can do a lot of these mechanical property measurements of soft tissues, like ovaries, teeth samples or tooth samples, and a lot of these other tissues on biomaterials. Before I go there, this is the basic principle of Indenter Systems, where mostly it's a depth-sensitive technique, and we acquire load versus the displacement in the vertical direction, and then you have a loading unloading curve. So during the unloading part of the curve, usually we do a fitting there and calculate the contact stiffness. And there is a software logarithms within the system that allows us to calculate the modulus and the hardness, keeping in mind or keeping in consideration the basically the tip area function. So you can see in this system, we can do both reduced modulus and basically the hardness, which is a peak load divided by the contact area. So this is the basic fundamental principles. Now, we do have the conventional systems, but in that system, we don't have a high-speed indentation capabilities. So right now, we can do almost, it take 3-4 minutes to get one indent, but with this integration of accelerated probe mapping that we installed last year, here it allows us, is basically a configuration of both software and the hardware modification. Here we can do almost 6 indents per minute. It's fully automated. And then we use the transducers to basically withdraw or do some of the actuation. And then it also has an integration of the piezo in it. So basically you can also do a mapping. So the piezo allows you to move from one spot to other spot. So it has a minimum, which basically minimizes your, drift and probe wearing. And then you can also do in a different environments. It has a closed chambers, so you can also do different temperatures. But this significantly allows us to do a very large area indent with a short duration of time. So, for example, if you look at this, this is a ceramic matrix composite, where you can see the left side is basically optical view, and then you can see it has the two components, matrix and the different phase components in different materials. So you can see the different contrasts here, and then you can create an array. So you can create a grid. You can create whatever you want, 20 by 20, 100 by 100. On the right, you can see basically a modulus map that gives a modulus and the hardness. So you can see here pretty easily, you can identify the different components within the materials in a pretty short span of time. And then this high-speed indentation also allows us to calibrate the tip area function, which is very important component in identifying the basic calculation of the modulus and hardness. In a conventional technique that we have, it usually take almost 4 or 5 hours to calibrate the tip area function, which we have to do a large number of areas, basically indents with the different pores, and it takes almost a while. But here you can do just within few seconds, and basically that means every user can have their own tip area functions, and then this allows them to properly basically calibrate the system or get a right amount of modulus and hardness variations within their samples. And then if you look at this here, uh, there is a plan there that we integrate this existing, or the one we have, the XPM, accelerated probe mapping, with the X probe also. So this is a MEMS-based probes, which allows us to go for a very low load. So you can go up to like a 1 or 2 nanonewton. So basically you can start indenting or mapping pretty thin, like a few nanometers. Right now with the existing configuration, it's not easy to do the mechanical measurements of a film sample, which is a thickness of few nanometers. So here it will allows us, even like you have a 1 or 2 nanometer films, you can basically map it. So on the extreme right, you can see the extreme hardness map, which looks pretty much like an EBSD map on the left side, with the same amount of collection time, but it's more quantitative information where you can find the variation in the hardness and modulus across your sample. So this is a pretty much overlapping technique with the EBSD. And then given the speed we have here, we can do in a pretty short span of time. So you are welcome to use this technique. We have this one available right now in the speed facility. And then we have the soft indentation capabilities also. So here we can do, you can see we can do up to pascals or kilopascals, ligaments, skins, tissues, hydrogels, any type of these things. So we are working with a lot of medical people in the downtown campus. They come here, and then basically I work them on a collaborative basis to get these measurements for them. Now, moving to the other technique, a pretty useful technique that's coming in a couple of months, is basically bringing the scanning Pro Microscopy and then the Raman together. As you see, the SPM brings a lot of information, especially when it comes to the physical characteristics of the samples, in terms of the topography, mechanical properties, electrical, magnetic properties. Our systems are fully loaded with this functional imaging, but it's a true nanoscale imaging technique, but it lacks chemical sensitivity. So on the right, you can see here, you can see electrical map of carbon nanotube. In the current image on the right, you can clearly see those high contrast region correspond to like a dope point fitting this carbon nanotube. Bottom, you can see some of the cancer cells. So, but you cannot find some sort of a chemical sensitivity here. And then this nanotechnology era, is very important that we should have all these capabilities integrated into a single system. So like a one-stop shop, when the user comes, you want to do the AFM, okay, you can do the AFM. You want to do Raman, you can do Raman. If you want to do chemical mapping, he can do the chemical mapping. So, but in the conventional Raman system is very specific to chemical imaging. Okay, so it's very precise structural information. It has a wide range of application. It's non-destructive, obviously, and then we have a large number of laser sources. The current system we have, the Raman system, we have 4 laser sources, and then the one that we are getting also have multiple laser sources. You can go from UV to IR, and then but it is limited. So especially you cannot go for a high resolution here. Some of the drawbacks are in low cross section, limited spatial resolution, because the type of the optics we have is in a limited type of resolution. So how we can increase that? So that's the idea, is that how we can increase the spatial resolution, what technique we should use. So here now comes the how we can then start bringing the AFM and the Raman imaging or Raman spectroscopy or a Raman PL type, how we can integrate them together. On the left, you can see here is a combined or the co-localized image of AFM and Raman. When you have AFM and the Raman system integrated together, in the AFM, you can do a normal surface topography, you can do a phase image, you can do a friction image, you can do a capacitance image, you can do a Kelvin probe, which is basically a work function measurement. So these type of things you can do simultaneously along with the Raman chemical mapping. So basically when you combine these two systems together, now along with the AFM advantages, now you are adding like a chemical identification or chemical imaging as a plus point in this integration system. But what about the submicron features? Okay, so can we image chemically any features like AFM can be always used, allows us to image features as low as like a nanometer, even less than a nanometer resolution. But can we, how we do it with the chemical resolution? Because we are limited with the optics of the Raman. So in that case, if you take a one single like a magnification of this is how the confocal Raman image looks like for that area. It's a blurred, obviously, it's like resolution. When you go to the terse on the right side, you can see the graphene oxide along with the carbon nanotubes on the side, and you can see a pretty sharp edges, pretty well-defined resolutions. So that's what the terse comes in when we try to advance towards a high resolution chemical imaging. This is the technique that we can do. So how it is possible? So what we should do? So terse is basically tip-enhanced Raman spectroscopy. It's a combination of SIRS and SPM. If you know the SIRS, surface enhanced Raman spectroscopy. So basically here you can use few nanoparticles, metallic nanoparticles, especially the gold and silver, and then can put the molecules on them, and when you do the Raman spectroscopy, you can significantly enhance the signal because of excitation of the surface plasmon resonance. You can have a signal amplification by a factor of 10 to the power 8, but still it's still a microscopic technique. But then on the other side, you see the SPM, which uses a pretty sharp probe, only a few nanometers, is give you pretty high AFM resolution, pretty high spatial resolutions. So the terse is basically integration of both. Here, basically, we use the specialized terse probe with the metallic coating here, the gold silver, and then that probe comes in close proximity on the sample surface, and we excite a laser, okay? We excite a laser on this probe, so that excites the surface plasmon resonance. So basically this probe is acting like an antenna. So that converts, the far field, optical excitation, far field energy, like a mediated transfer of a far field energy into a near field, which is called the evanescent field mode. So basically you are creating a hotspot here, which is a non-propagating field. And that allows you to significantly enhance or amplify signal. And then we scan the sample underneath this probe, and then the volume of that scan is pretty small, almost the size of the probe, like a few nanometers. So in this way, you can basically chemically identify, or you have a chemical identification or Raman signal from that very small volume cross section that you can collect. And in this way, you can significantly enhance your spatial resolution in this third spectroscopy. Okay, so if you see here on the left side, so basically it's a combination of a Raman SPR to get this nanoscale resolution. We confine that plasmon resonance within that small spot, hot spot, which is basically right underneath the peak sample junctions. And then you can see on the left is basically a detailed configuration, how we can do this thirds in the reflection mode and in the transmission mode. And then you see a hot spot, which basically enhance your field. And then you can see how you are scanning here. And then while scanning with this probe, you can have an amplification of Raman signal by this such an order of magnitude. You can see you're scanning carbon nanotube, you generate basically the chemical map of this carbon nanotube, followed by the spectrum of that. So this is basically the principle of this third system. And then mostly the nano Raman AFM integration thirds is basically for the 2D world. So 2D materials are basically the most beneficiary out of this technique. And a lot of people have also start doing research for like identifying the viruses, monolayers, like a soft material also. But the best thing to do here is the wide range of these 2D materials with this type of technique. So if you see here, this is an example of a 1D material carbon nanotube. Why we need to use thirds? Because obviously this is required a pretty high spatial resolution. And then here you can see the example of a thirst map of a single carbon nanotube. And on the right, you can see the spectra you can get. And you can easily identify those, D bands and G bands. So basically the ratio of these will give the amount of defects within these materials. So you can get both a map and you can get a spectra. And then it's pretty high speed. So you can get pretty quickly these spectra. And then this is the type of system that we are getting here. This system is fully loaded system. We have tried to include the users' needs. We spoke with the users. We tried to incorporate all these needs, but if something is missing, we can always add over a period of time. If you look at the different AFM, what the AFM capabilities within this configuration provide on the topography, stiffness, or mechanical properties, you can do surface potential, capacitance measurements. Basically, you can do a carrier concentration. You can do a photocurrent measurements. So it's fully loaded AFM with all functional capabilities. Then we have an environmental chamber here, so you can do at a different. You can have a different environment, so different gases, and also heating and cooling stage. So basically, you can do it at different temperatures. You can do liquids. Then we have a high-end Labram AFM integration here with such laser configurations. So you can do the thirds. You can do conventional Raman spectroscopy. It has a edge filters, so it also has a notch filters. So notch filters will allow you to do both strokes and anti-strokes. So basically, if you know the strokes and anti-strokes, if the ratio of these two spectrum will give the information about the nanoscale thermometry, basically charge transport at a nanoscale, you can identify. And also allows you to do the Raman spectroscopy at a low wave numbers. You can go down to five wave numbers, so you can start seeing also the metals. And then it has 4 different lasers. And then it's a fully integrated system. So you can do simultaneously the AFM Raman, or you can also do AFM separately, or you can do the Raman separately. It's with the third integration also with this the different detectors, so you can do PL up to 1.6 micron. So that system will have in a couple of weeks, a couple of months. And then I'm just we'll talk about touch base with a few of the applications here, like a 2D material. Why we need to use TERS, because we need to identify both in terms of the defect density and also the resolution, the type, these type 2 materials required. So you can see on the left side is basically a TERS map of D bands, then B is the right side is a topography, and then the lower left is basically the spectrum and also the distribution of the D to defect densities, the bottom right. So basically you can identify, the ratio. When the ratio increases, the defect density increases. So you can do these type of measurements with this technique. And then you can see here, you can also do a mapping of these 2D materials, white TERS, because if you do a conventional Raman imaging on this image shows that a Raman map of a 2D materials, different layers, different types of 2D materials. So basically you cannot identify the different components, but when you do with the TERS, you can identify the different heterogeneities in these materials. You can identify the different phases, different components. So you can also see the resolution also improve significantly. So this is how this type of technique is very important. And then you can find point defects, grain boundaries, dopants, wrinkles, strain, presence of different materials in its alloys. At the same time, this is an example of a combined AFM and Raman together. So you can see you have a topography image in the second one is the TERS image mapping, and then capacitance, Kelvin. So remember, you don't need to have two different types of system to do these things. You can just do at one place with a high resolution. Then, okay, so some of the other applications that I have not included, but you can also do like a semiconductor nanostructure, stress profiles, strain variations in those materials. You can do that. Some of the groups have seen viruses, the single virus you can detect with this Raman spectroscopy. So what I can say in the summary is that the TERS is a combination of, by the way, we are also getting the scattering SNOM, scanning near field optical microscope. That's also a part of this, the instrument that comes. So TERS is basically is a combination of both SNOM and Raman. In the SNOM, you can get a pretty high optical images. Basically, you are breaking that the limitations of a 0.5 micron optical resolution with a far field optics. Here, you can optical resolution. You can go down to few nanometer with SNOM, so you can see the plasmonic effects in these 2D materials. So that's also a part of this system. And then the TERS is done with an AFM Raman system. So you can do a co-localize these measurements. You have application for 1D materials, you have application for 2D materials, both in terms of TERS and the mapping and the photoluminescence capabilities, along with the integration of different SPM modes. And then this will also allow you to do a feasibility measurements, basically the mechanical strain in semiconductor nanostructures, nanomaterials, viruses and biomaterials. So it has a wide range of applications. And then we are looking forward to have these systems in our facility. Thank you.
If anyone has any questions, feel free to unmute yourself and ask or put it in the chat.
I have a small question, GS.
Yeah.
So what do you think about, like, I mean, when you said like the minimum resolution of TERS is like few nanometers, is it possible to look into like point defects or something? I know it's a high ball, but
Yeah. I think that the TERS probe they are making, they say that they have gone down to 8 nanometer, especially the actual resolution is 4 nanometer, but especially there is also some convolution effect on the probe.
Okay.
So 3-4 nanometer and the step size of 1-2 nanometer, they have seen it. And I'm hoping that we can see the defects at that low scale. But unless we do those measurements, we don't know. But the company still says that it's possible to measure those defects.
Okay.
Yes.
Yeah.
Yeah, seems your truss, that is the configuration, is like a regular Raman plus or AFM, some configuration, right?
Yeah, yeah.
Yes, it's bigger than like addition of the current one, Oliver Raman.
Yeah.
So if that is, for example, nobody use the truss, that rest part still can use as a regular Raman?
Yeah, so they can use as a regular RAM. And here the advantage is that we also have a software control filter. So we have a edge filters and notch filters. Edge filters we have in the current Raman system. So edge filters will allow you to, it doesn't allow you to measure the anti-stokes, okay?
Okay.
And also you cannot go beyond 50 wave number, but here the notch filters will allow you to measure both stokes and anti-stokes, and you can go down to 5 wave number. So you can just switch with the software setting, these two filters.
Okay, I noticed that you have like 5 different wavelengths. That is like 850, like near IR and laser, right? Yeah.
Yeah.
Yes, that is a lot.
So basically, yeah, if they want to have those stokes, anti-stokes, they want to measure nanoscale thermometry at the nanoscale, then they can use this system. It's not necessary you have to do it together. You can do it separately.
Okay. Okay, sounds. And for the truss training, they need like after the regular training or just combine together?
Yeah, so mostly if that system is designed, if they want to do TERS, so then we can train them. But if some users comes, okay, we want to use those Bragg's filters, do anti-stokes, and then also they don't need to go for TERS training.
Yeah, I understand it seems they need like experience both Raman and AFM. If they know both, maybe easier to understand the trust, right?
Yeah, that's true.
Okay, thank you.
One more thing, Jia. So you were talking about the low temperature and high temperature experiment. So the stage will have the capability from what temperature ranges?
Yeah, so the right now we have the LinkedIn stage, but that has the range that but we are trying to acquire through core facility proposal. We already have the proposal in the pipeline. Let's see, where we have this liquid helium stage. Okay, so where you can go down to, I think, -4 degrees Celsius to 750 degrees Celsius, and then you also have the capabilities to apply the magnetic field.
Okay, great.
We have that stage, that can be integrated into this system.
Cool.
There's no more questions. Anyone have any last call? All right, well, thank you everyone for coming. Be on the lookout for information for our April Tech Talk. It will be hosted by NewFab. If you have any questions for GS that you didn't get a chance to ask or you think of later, please just send in an email. You can find his contact information on the Nuance website. Okay, thank you.
Okay, thank you.